Hi, in the previous lecture we talked about the Lagrangian equation. It is also called Euler-Lagrange equation. And without deriving it yet, solve some examples on it using that idea. And that example, that formula, let me write it again on the board, was the following. This kind of equation. And L here, L was the Lagrangian, it was called Lagrangian, and it was the difference between the kinetic energy of the particle and the potential energy. Not the sum, as in the case of Hamiltonian, but it is the difference. But we didn't derive it in the beginning. Now we will try to show this equation, why we can use it, and also the concept of action and stationary action principle. Stationary is maybe the better word, correct word, is the word that fits the situation better, but it is widely known as least action principle. It doesn't have to be least, but in some cases something is minimized or maximized. Or, as we see, some optimal result can be obtained by this principle. It is not a simple maximum minimum problem, just to take the derivative of a function with respect to the, for example, if we have a function, for example, a function y is equal to f of x, for instance, and let's say it is such a function given by some mathematical expression. But there are some minima and maxima, for instance. This is a local maximum, this is a local, another maximum, this is local minimum, etc. If the function is given by some expression in terms of x squared, x, and constant, etc., then we can simply find these critical points by simply taking the derivative of y function with respect to x and setting to 0. You can find the critical points, but this one doesn't give us the all the maximum, minima, or inflection point. For instance, the inflection point may be the following. This is a case of y is equal to x cubed function, for instance. So, unlike the first case where we have a maximum, we have two maxima and one minimum, here we don't have a maximum nor a minimum. However, there is a critical point here where the slope is 0, because here, if the slope is 0, we can find the critical values of, let's say, maximum and minimum points, or if there is any inflection point. Here, for instance, in the case of the x cubed function, we neither have a minimum nor a maximum. However, there is another critical point, there is just maybe one critical point, which is at the origin, where again the slope dy by dx is again 0. So this is called inflection point, etc. So in simple mathematical analysis, for example, we can just by setting this slope, because if the slope of a function is 0, it means it's a horizontal case. If it's horizontal, it can be either a maximum like this one, or a minimum like that one, or an inflection point like that one, but it is neither a minimum nor a maximum. Alright, so this by itself doesn't give us which one is maximum and which one is negative if you have more than one value. However, if you take the second derivative, let's say d squared y by dx squared, and set it and put here, not equal to 0, but these critical points can be placed here. If the second derivative is positive, it is a local minimum. If it is negative, it is a local maximum. If it is still 0, it is an inflection point, etc. But this is something else. Today we are not talking about these preliminary properties of functions, but instead we will talk about the functional, because we will have a function of a function. However, here y is just a function of x. So this L is defined as Lagrangian. But in the history of science, for instance, Euler and Lagrange. Euler in 1744, Lagrange in 1788 found out these subtleties, these details of those functions, etc. So it is also called Euler-Lagrange equation. This equation, sometimes called Euler-Lagrange equation. In the case of Euler's function, Euler's analysis, we don't have kinetic potential energies only. We can apply it to any such case where we want to maximize or minimize some quantity. But that quantity is not a function, let me repeat, just this, like this y. It is maybe a function. Now we have a functional. Functional means function of a function. In which fields of physics, for instance, can we, as a physicist, we first of all try to apply the mathematical equations, some auxiliary tools in some physical cases, physical problems, first of all. So it is applied, as in the previous lecture we have seen that this formula can be applied to several interesting cases. Today I will also try to give some other cases soon, but first let's try to understand how we obtain such an equation. And in Euler's case, we generally have some, let's say, a j. I will try to explain. It is an integral from some initial value to some final value. And here, for example, we have an f, but f is a functional. F is a function of, let's say, y prime, and maybe time dependence or x dependence, and dx, for instance. So this thing, j is j, that integral as a whole is optimized or minimized, maximized. J is to be, let's say, optimized. Let's call it minimized, for instance. And then around 40 years later, Lagrange used it or applied it in more physical cases where we have the kinetic and potential energies of the particle, or kinetic and potential energies can be written for the particle. So let me immediately give a simple example to this J, for instance. What do we mean by minimizing or maximizing a quantity? One of the important problems in history was Brachiostochron problem. The Brachiostochron is a combination of two words in Greek. The second part, as you may easily understand, is chrono, means time. Chronometer is derived from that. So this part is the time part. And this brachistos part, in this case, corresponds to least, minimum. So least time, but for which case? Let's consider a basic situation now. For instance, if we have a kind of rope, or if you throw something into the air, for instance, we take a certain ball and just throw it from an initial point x1, y1 here to a point x2, y2 over there, or somewhere lower than the initial point. If you throw this with an initial velocity, we know very well from preliminary things, from previous physics, elementary physics courses, we know that it follows a parabolic trajectory. It's a parabola. And the parabola is, for instance, as we see in one of the examples today, a parabola, for example, is, let's say, a constant times x squared is a kind of parabola. So if you plot something, for instance, this is a parabolic curve. In this case, let's just turn it upside down, for instance, and this is a, if you take it the other way, you take the symmetric one, for instance, and rotate it, you get a curve. This is in the form of a parabola. So we know this already. But why does the critical point here, why does the ball follow such a track to arrive from the initial point to the final point? There are millions of other choices for the particle, but why does it choose this very one that we see on the board, or a parabola? If you change the initial velocity, it follows a different parabola and at the end arrives at a different point. But in every case, from the beginning to the end, it follows a certain parabolic curve. Of course, we can prove this by other means, writing the motion in the y direction and x direction separately, and by just making use of one and plugging it in the other, you can easily get that it is a parabolic curve. In Physics 101, we do it. However, here in classical mechanics, we go one step further and try to understand why that principle, Lagrange equation, is applied, and how we obtain that function, Lagrange equation, and in relatively simple mathematical terms, and then apply it again to some other examples. For instance, let's say this is the, let's turn upside down the axes. So let this be, for instance, x-axis, and this one y-axis, and assume that this is the beginning, initial point, and here is the final point. Let's say a bit lower than that. The first one is called x1, y1. Second point has coordinates x2, y2. And between these two things, we will send an object. Let's say a ball or any other package. Can we immediately say that what is our purpose? We want to carry out this transition or this transportation in the least amount of time. There are billions of infinitely many number of ways from the initial to the final. You can choose any path you like, but only one of them corresponds to least time for this transportation. And assume again that it has no initial speed. It is just because it is at a higher position at the beginning than the final position, it has a tendency because of gravity. Gravity is not the only thing, it is the force field. This point particle, or any particle we will send here, is in a force field. What is that force field? It is the gravitational field, G acting down, or any other. For example, there may be some other electric field for a charged object. This is the same idea. But for simplicity, we talk about more mechanical examples, so that there is a field of G acting down, gravitational field, and we have a simple object having mass m, and we will try to send this object with no initial speed, zero initial velocity at the beginning, so it will arrive at here. Let me immediately first of all say that the path that we have to find is not a line. If you draw a line between initial and final points, yes, of course, it is the shortest time. But be careful, keep in mind always that shortest paths do not necessarily correspond to shortest times. Yeah, if you draw a line here joining these two points, the shortest path which can be drawn on this board is a line, of course. But we are not interested in the shortest path, we are interested in shortest time. But that shortest time, as we will see soon, is not obtained for linear paths. Instead of that, we will have a different curve. It is not a line, it will be a curve. But which curve? Do we recognize that curve? You will see. It is not a quarter of a circle either. For example, it's a circle. If you draw this quarter, for instance, this is not the curve which is put here to give the least time. It is not a line either. Neither a line nor a quarter circle. It is something else, as we will see. Now, what is the purpose? Let's first draw that. There is one possibility. Let's say this is the optimal one. It is not a line as I try to draw. It is not a, it's a curve. This is the, let me say, this is the optimal curve, optimal function. And it is, let's say, y of x, certain x0, for instance, or a certain function. Because x0 is a function of time also. x0, it is, let's say, y of x0 of t. Since it is a function of a function, y is a function of x0, which is also a function of time. So we have, as we will find soon after the derivation, this curve, which is the optimal one. But all others, which are very nearby functions, maybe this one, or that one, or that one. All others, black curves, are necessarily a bit longer. Longer means not the length, but the if you choose for sending this particle a curve other than the red one, the time at the end will necessarily be longer than the minimum time. So this J is called the action. So it's a functional. It corresponds to the action in Lagrange's equation. So F is dependent on both the y variable, because y is the vertical, because of the position, as we see, and y prime is the correspond to the velocity, and also this can be written as y prime x, or as we see in the Lagrangian will depend on let's say x dot and time also. This is the Lagrangian L will correspond to this f, and you want to optimize, minimize that. And it is either a minimum or maximum or a saddle point. It's this can be either a maximum or a minimum or a saddle point. What is a saddle point? It is like the saddle of a horse. It is not quite easy, but let me draw the picture for that. It is a saddle of a horse. Not doing very nicely, but try to understand that it's a saddle, and the critical position is just at the middle, because there are two opposite slopes, curves here. One of them is this curve. So if you look through this angle, if you look at that, then this red one is a concave down curve. So it is a sort of local maximum. But if you look at it the other way, this is the concave up curve, so that we have both a local maximum and a local minimum depending on your angle of looking at it. So this is also a saddle point, just like the previously. I have previously drawn an inflection point. This is neither a minimum nor a maximum. So here we have both a minimum and a maximum at the middle of the saddle point, or simply a maximization or minimization is carried out in such processes. And in this case, we will soon apply the idea to find the curve which corresponds to least amount of time for that transportation from the initial point to the final point. If we consider the previous case as a concrete example, for instance, this is the for instance, optimum curve, so that we are interested in the nearby possibilities, and those nearby points can be investigated by the following trial. Let's say xa of t, xa of t is x0 of t plus a times beta of t, where a is a number parameter, where a is a number, and beta of t is a function, is an arbitrary function. Arbitrary, but we only know that at the end points it becomes 0. So that it doesn't affect the initial and final positions. Since this is 0, at the ends, at the beginning and at the end, xa and x0 are equal. However, in between, what happens? What is beta of t? It's an arbitrary function. So we also know the boundary conditions for beta. Beta of t1 and beta of t2 are both 0. And we want to find the change of s as a function of a, because this is a number. However, it is a number we can change. Assume we can play with this a. So the functional action, the action a or s, is in general an integral, like this j, capital J, as I erased here. So this a or s, s of x of t, s of x of t, let's say, is an integral from the beginning to the end, t1 to t2. Here we don't have time, but in the case of Lagrangian, we have the time, initial time, final time. We will have energies to introduce the capital L, which is the Lagrangian. So in this case, we will have simply L of x, a, and x, a dot, and let's say dt. And we want to see the change of s for a change in a. We want to see the change. Yeah, this is just del by del a. Let me repeat, a is the number parameter that we write here. Del by del a of s of xa of t, the function of s, which is called action in such cases, is an integral of, let's write the del by del a here, del by del a integral L of xa dot and dt. Of course, derivative and integral operators are interchangeable, so then you put it inside the integral. But let me talk about one other thing for these differentials. In general, if a function, let's say z, depends on two variables. A function z is a function of two independent variables. X and y. So we can write then z is a function of x and y. So if z is a function of two things, then what happens to z if both x and y change by little amount? Then let's say dz is a function times little amount and another curve and little amount. So here we have del z by del x, and here we have dx, and del z by del y multiplied by dy. So if both of them are changing little by little, for instance, very small increments dx and dy, then since we know how z changes as a function of x or as a function of y separately, just this little dx multiplied by the way it changes, which means the derivative, the slope for that change, and multiplied. If there is no change in y, this term is simply 0. If there is no change in x, this term is simply 0. But if both are changing by little amounts dx and dy, this is the general idea. So apply this simple idea that we know from, at least from statistical physics in thermodynamic functions. Alright, if you apply this simple idea to the case of the Lagrangian here, and this derivative is now applied with respect to x and xa and xa dot, what happens? So that this del by del a s, let me simply write s. It is an integral where we have one term del L by del A, but we multiply by del XA by del XA, and also del L by del A, and now we have del X A dot by del x A dot, all multiplied by the small time increment dt. So in fact these red fractions are 1, so we didn't change anything. However, now we can write them in a chain rule manner. So let's just change the places of these terms. So we can have an integral, of course, from t1 to t2. dt is the increment here. So we have del L by del XA multiplied by del XA by del A. Next, del L by del XA dot multiplied by del XA dot by del A, and all multiplied by this dt. But we have the as I erase here, let me rewrite it. What is the relationship between xa and a and beta? Remember that xa was, or xa of t, because it's a function of time, was x0 of t plus a times beta of t. This was the expression that I written a minute ago. So a, the new form, is a function of a, of course, because it's a number that we can play with. Beta of t is an arbitrary function, and x0 corresponds to the optimum case. So, if you use this last expression to find these partial derivatives, you can easily get beta and beta dot, as you will see. So what about first circle? Del xa by del a. If you take the derivative of the left hand side with respect to a, since it doesn't depend on a, here a is like a variable beta of t. Forget about of t, it is beta. Let me show you a relatively easier notation. So that del x by del a corresponds to simply this beta. What about the second derivative, partial? So del x xa dot with respect to del a, if you take the derivatives time derivatives of both sides. This will be xa dot, this will be x0 dot, that will be a and beta dot. But this is not dependent on x, so x dot with respect to a gives us beta dot. So that with respect to the position it gives us beta. With respect to the velocity with respect to a is just beta dot. So now let's write this expression again. Let me call equation 1. Rewriting equation 1. So start with this equality. On the right hand side we have, forget about the limits right now, del L by del XA. Del L by del XA multiplied by beta. Plus del L by del XA dot multiplied by beta dot, all multiplied by dt. So we arrive at such an integration. How do we go further? Let's consider the second part. Let's call this first part, second part. Leave the first part aside and consider the second part. Now consider part 2. Just the second. We will come back to the first. What about the second integral? Let me just write it separately. This is an integral between times t1 and t2, and we have del L by del xa dot multiplied by beta dot and dt. It is not very easy to see at the beginning, I'm sure, but if you look at it more carefully, it reminds us integration by parts, because there are two parts basically. There are two parts like integral u dv. If you try to see this as a product of u dv, a function and the derivative of another function, then we know how to get such integrals. Then applying integration by parts, what do we get? uv minus integral b du. Because if you have a derivative, an integral like u dv, it is, remember, uv minus integral v du. I'm not writing the limits, but if, for example, if these are t1 and t2, these are also t1 and t2, t1 and t2. So, but which one corresponds to u, which one corresponds to dv? This part corresponds to u, this part corresponds to dv. So that uv minus integral v du, if you write it this way, then we arrive, I hope, somewhere. U, let me consider this one. U and v. What is u? Simply del L by del xa dot. Del L by del xa dot. Multiplied by v. But what is v? V, if dv is, if we assume the second part as dv, then the integral part simply becomes beta. It's simply, then v is simply beta. So we have a beta here between limits t1 and t2. Next, we have this second part. Again, we have a beta for this v, and du is simply time derivative, because if you take the derivative, it becomes derivative with respect to time. So we have the second part, d by dt of this part, which is del L by del xa dot, and a dt. What about the first? let me call this part as third part. If they are 1, 2, these are 3 and 4. What about the third part? Third part is simply 0 and 0 because as we have assumed that somewhere here, the function beta gives us a 0 both at the initial and at the final points. So since beta of t1 and beta of t2, we are not interested in the first parentheses because the second third beta here makes it certain that it is indeed 0 at the limits, and these are the limits we have to apply. So beta of t1, beta of t2 are both 0, so that there is no contribution from the term 3. What about term 4? But we also have now, second is written, so we have 1 and 4. Now we are left with 1 and 4. First part, which we left aside, and this last part. So if you write it, let me rewrite number 1 here. Number 1 minus number 4. Number 1 is that what is on the left hand side, by the way, we started with, remember, del by del A of applied on S, x of x A of t, functional. On the right hand side, we only have two terms, first block and fourth block. First block is simply integral del L by del xa and beta minus fourth block, which is this thing, minus beta, and let me write it later, d by dt del L by del xa dot multiplied by beta altogether. So this is also dt. As you see, beta appears in both of them, so we can take it out. Beta can be taken out, and after that we have, let's say, del L by del xa minus d by dt del L by del xa dot altogether multiplied by d, but this has to be equal to 0 at the end because we assume that the action which corresponds to the stationary value, stationary it doesn't have to be least, but the more widespread known, widely known name is least action, but the better word, as the physicists call it, is stationary action. If something is stationary, it doesn't have to be necessarily minimum. Other possibilities are maxima and saddle points. Alright, this action has to be, in this case, minimized so that the right hand side should be 0. But since beta cannot be 0, since beta cannot be, or does not have to be 0, not cannot, but does not have to be, because beta is an arbitrary function. It is 0 only at the endpoints. Since beta is 0 only on the endpoints t1 and t2, it is not 0. So we can neglect this beta. So the only possibility for this integral to be 0 is that this quantity inside should be equal to 0. Since beta is 0 only at the endpoint points, we can leave it aside. The only possibility for the integral to be 0 is that the inside is 0, and that what is inside? we can write it this way or the other way. Let's first, according to the better known form of Lagrange's equation, let's consider it here. So it is written as d by dt del L by del xa dot minus del L by del xa, that's equal to 0. xa is anything. For example, in some problems as we have drawn solved in the previous lecture, this xa can be a generalized coordinate. In some cases it is the radius r, as we will see in the following examples. In some, let me write it as a note. xa is a generalized coordinate. In some cases, it is, let's say, simply x component. In some others, it is, let's say, radius r or some angle theta. So we can have also other possibilities. So x doesn't have to be necessarily x component. It is a generalized coordinate. According to the geometry of the problem, this variable, it is a variable which affects the energies, for instance. It may be the x-axis, y coordinate, x or y, or some radius r, or some angle theta. In certain problems there is only one such variable. In some others there are more than one variables. We assume all of them are del xa or xa dot. Now let's go back to the Brachistochrone problem and find the curve that fits, that gives us the least amount of time to reach the final point starting from the 0 position. Now we will find the best curve. Best means it is the one that gives the least amount of time. For instance, if you choose a directed line segment for this little band, let's assume it's a bead, and from the initial point up there to the final point down there, we leave it, and if you choose a directed line segment, at first sight it may seem to be the best choice. If you leave it along a directed line segment, it arrives in minimum time. You may think at the beginning, however, it is not the line, as I said before. So let's try to find what is the correct shape of the curve that gives us minimum time, least amount of time in the Brachistochrone problem. So let me write it as an example. The Brachistochrone problem, the Brachistochrone problem is related with the minimum time, the least amount of time for a particle starting from initial position. Let's assume it is the origin. It doesn't have to be, but for simplicity, let's assume it is the origin. A time for a particle starting out from initial point, let's say x1, y1, 0, 0. Origin, for simplicity. Okay, starting out from initial point x1, y1, ending at final point x2, y2, So problem is related with the least amount of time for a, so time for this second part, least for the first part. So that's the, is our purpose. That problem is related with the least amount of time for a particle starting out from initial point x1, y1, ending at x2, y2. So let me draw a simple picture for this. For instance, let's choose the axes, xy axis. And here, the particle is there, the object of mass m. For a particle of mass m, which starts from the origin. This is the y-axis, that's the x-axis. And the final point is here. So we will find the general shape of this curve. Alright, now we need the Lagrangian. First of all, let me say another thing about the Lagrangian and action in general. Action. In general, action, does it have a unit? Sure. So what is the unit of that? Like it is del L by del T, kinetic energy minus potential energy. So the action A or S, we have used S in the previous analysis. The action S has the unit what? Lagrangian times time. So remember that d by dt del L by del x dot, or del L by that into del L by that position, for instance. What is that? Energy over so joule, for instance, joule per energy, joule per meter. But we also have remember that d by dt del L by del x dot. So that this term corresponds to L is just the difference of energies. So we can write it as energy per meter per second times second. So this is the corresponding quantity. So joule second is the unit for action. Joule second is the unit of action. Do we remember this joule second from somewhere else? Sure. What is that? Planck's constant H. So the unit of action, joule second, Js, is the unit of action. For instance, Planck's constant H is, remember, 6.6 10 to the minus 34 times joule second. It is also an action, but the amount is very little. So this is outside the scope of this course. However, you can make a matching between Planck constant H and the action. Because remember that here in this analysis, actions are S, that integral. Okay, the integral S was these L's, del L by del x a minus d by dt del L by del x dot and times dt. So this corresponds to the unit of joule second, which is the unit of action. So let's come back to the case of Brachiostochron problem. Okay, what about the energy of the object at the beginning? x1, y1. x1, y1. 0, 0. And this is called x2, y2. that we want to minimize, for instance? It is the time. The quantity in this journey, let me call it journey, little trip from the beginning to the end. In this journey, the quantity we want to minimize is the time. In this journey, the quantity we want to minimize is the time. What is that time? That time is found by an integral. What is that integral? If this is the curve, for instance, it has to follow, you can divide this curve into maybe 1 million pieces. Like a stroboscopic process. So we divide it into maybe 1 million short intervals. So each interval is ds. That length, path length, is ds. This is little, it's not capital S for the action. Okay, ds. But if you look at it in a magnified manner, for instance, in a magnified manner, so this is the part. So this is, let's say, ds. But that ds is like the hypotenuse of a little triangle. So that we have this part and that part. This part is ds. It is almost like a line. But the others are dx and dy. Or, yeah, the dx and dy. So in a way, ds is the hypotenuse of this little triangle. But what is the time t for this? This time t is the integral of small dt's. And dt is the time to cover this ds. And if you add up very little time intervals from the beginning to the end in an integral manner, you will get the total time. And this is the quantity we want to minimize, applying this principle. Is simply integral dt, but that dt is again ds over v. V is the velocity. V is the velocity in this path element. Of course, v will change. That little v velocity is changing throughout the motion, so it is a variable. ds is that little segment, and that segment can be written using Pythagorean theorem. It can be written as, for instance, ds can be written as dx squared plus dy squared. So we have this right hand side for the numerator. What about the denominator? Also from again, go back to physics 101. So the formula v squared is equal to v0 squared plus 2gx, 2gy, x-axis. Let's use x-axis for the vertical and y for the horizontal. And there is no change here. And assume this is the x component because we are rather interested in the vertical motion. So let's use x as the vertical variable, positively increasing downward. And since there is no initial speed, it starts from zero speed, from point zero with zero speed. So v can be written here as v is equal to root 2gx. So put this v to the denominator and this ds in the numerator. Then we have t, which is an integral. In the numerator we have root dx squared plus dy squared divided by root 2gx. Next, we can multiply and divide each of these terms by dx squared. So we can write it here as dx squared by dx squared, dx squared by dx squared. And of course, we multiply by 1. So what do we get by this little trick? So the first term is just, we can take this upper dx outside as dx. So t will be integral. In the root we have just this fraction, which is 1, plus dy by dx, which is y prime squared. Outside we have a term dx divided by root 2gx. And where, of course, y prime is simply the derivative of y with respect to x as usual. There is no time dependence, let me repeat. This is just for the positions. Time is only written appearing here as the quantity which has to be minimized. Alright, now let's go on from this step. What do we get here? Let us take this part also outside, because it's a constant and it doesn't affect our analysis. Since root 2g in the numerator, not x, but root 2g can be taken out without any effect on the analysis, since 2g can be taken out without affecting our purpose, let's say. So we have integral, forget about root 2g. What do we have next? 1 plus, let me write it separately, 1 plus y prime squared divided by root x, and here we have dx. And this is the quantity to be minimized. This is the quantity to be minimized for this purpose. Let's call it f. Quantity f. It is not a Lagrangian. There is no kinetic potential energy, etc. It is a certain functional f. Because it is also, it's a function of x, but x is also a function of t, so it's a functional. Therefore, apply the idea of Euler's equation. Lagrange's idea, but Euler's equation for the functions. Then Euler's equation can be. But for this purpose, we need two derivatives: del f by del y and del f by del y prime. Let's first write f. This little f is simply root 1 plus y prime squared divided by x. Then, what is del f by del y? Why do we need these, first of all? Of course, we will put them in the expression. Remember, d by dx, del f by del y prime minus del f by del y equals 0. Because remember, if you compare it with the Lagrange equation, here we rewrite the Lagrange's here, d by dt del L by del x dot minus del L by del x equals 0. If you look at it carefully, there are some matchings. For instance, x dependence, t dependence, they are corresponding. F is L If x is now corresponding to y, then x dot corresponds to y prime. So they are just comparable and matching parameters. Alright, now let's find these partial derivatives. What is del f by del y? Since we do not see any y here, it is just 0. But we see y prime, so there's the other derivative is not 0. Del f by del y prime. What is the derivative of this? Let me first write 1 over root x outside. Here we have 1 over, remember that root x, if you take the derivative, becomes 1 over 2 root x. So root something becomes 1 over 2 times root 1 plus y prime squared multiplied by the derivative of the inside, which is just 2y prime if you take the derivative. So these 2's will cancel. So that del f by del y prime is simply y prime over root x, let's put it inside, x times 1 plus y prime squared. And now we obtain this part. So we have to apply d by dx also. Apply d by dx to this thing. D by dx applied on this right hand side, y prime over the denominator, is just 0, because at the end you will equate it to 0. But we can integrate both sides, we can apply the integration both sides, so that for we will neglect this dx, but then this will be a constant. Not important, but it's a constant. Then, after the integration, y prime over root x times 1 plus y prime squared is just a constant. But here, for this constant, we will not simply write, let it be A or B or C. Instead, for later simplification, we choose another constant. Let that constant be 1 over root 2A, for instance. 1 over root 2A. For, let me say, later simplification. Because if you simply write, let it be a constant C, then the rest will be more complicated. So, in order, or in favor of later simplification, we will choose a rather peculiar constant, 1 over root 2A. What is A? A is a constant. But this is just 1 over root 2A. So let me rewrite what we get at the end. Not at the end, but so far. So y prime over that corresponds to 1 over root 2a. So that y prime, so let's consider here, y prime over root x times 1 plus y prime squared is now 1 over root 2a. So if you take the squares of both sides, this becomes 1 over 2a. Squaring those sides, squaring both sides. On the left we have y prime squared divided by x multiplied by this parenthesis is equal to 1 over 2a. Then rearranging, so we simply multiply these. So we have y prime squared multiplied by 2a on one hand, so on the other hand we have x times 1 plus y prime squared. So y prime squared multiplied by 2a minus x. On the right hand side we only have x. Therefore now take the roots of both sides. Then simply y prime is just root of x over 2a minus x. But y prime, by definition, is dy by dx. Y prime, where is it? Y prime is just a normal derivative. dy by dx. Y prime is also called equal to dy by dx. So let me write it here. dy by dx is now root x over 2a minus x. Then we will, of course, as you expect, take the integral. So that y is an integral of the right hand side. What is that integral? So y will be integral, dx comes there. So we have root of x over 2a minus x and dx. So now there is one more trick here. Again, we will multiply and divide by the same thing, x, to make it, put it in a square form so that we will apply some trigonometric substitution. To make a trigonometric substitution, we multiply and divide by x. So if you multiply by x in the inside, then what do we have? Y turns out to be, this becomes x squared and we can take it out. So we have an x simply. X dx divided by what? Divided by root 2ax minus x squared. Now, what is that trigonometric substitution? Let's apply the case where let a be x be, let x be x equals a times 1 minus cosine theta. So this analysis requires some tricks, mathematical tricks to find the required result. Let that x be this one now. But if x is this, then what is dx? Then, of course, dx will be a times derivative of the inside. What is that? Cosine will be minus sine, but there's one more sine, minus a times sine theta, but don't forget d theta as well. Then our integral becomes, so our integral becomes what? Y is, instead of x we write a times 1 minus cosine theta. Instead of x. Instead of dx, we write another a times sine theta d theta divided by, inside we have 2a times x, what x is this? 2a times a times 1 minus cos theta, close the parentheses, close it again, minus x squared, which is the square of this, a squared, 1 minus cos theta, quantity squared. It seems to be complicated at this level, but as you will immediately see, it is not difficult, because several cancellations will occur, showing that only a very simple result. At the end of this integral, very simple result will be obtained. First, let me rewrite it, focusing on the denominator. And let it be y equals integral. So a times a, we have a squared here in the numerator, times 1 minus cosine theta times sine theta d theta. Relatively easy. What about the denominator? We have in the root, open the parentheses, so this is 2a squared for the first term. 2a squared minus 2a squared cosine theta. 2a squared once. Now let us solve some examples using these principles. A bead of Mansan slides along a parabolic curve defined by z equals b times r squared, where r is the distance from the z-axis and b is a constant. Part A, write the Lagrangian. Let's first consider the rotation of this system. The wire in the shape of z equals b times r squared turns around the z-axis at a velocity omega, angular of course, at an angular velocity omega. A, write the Lagrangian. And B, find the value of B for which the object B is turning in a horizontal circle of radius r. Find the value of constant B for which the bead is turning in a horizontal circle of radius r. Now, first of all, what we are talking about is the following. For instance, this is the wire, as I will try to draw on the board. This is the wire in the shape of a parabola, b times r squared. If you leave this ball, b, it just immediately slides down, we notice. There is no friction. So in such problems, we assume always that there is no frictional force. So because there is no distributive force like friction, when you leave this ball at any point, it just slides down. We are not sure whether it is the least amount of time as in the previous case, but it slides down, we are sure about it. However, if you try to rotate this this system, of course, the lower point is fixed. It is the origin. This point is fixed. But the upper part is the z equals br squared in the form of that function. If you turn this curve y sufficiently quickly, then this object may remain at the same position with respect to the y, which means it can complete circles. This is the z-axis. This ball bead can complete fixed radius circles. What should be that constant? Or you can be asked in the opposite way. Maybe b is given, let's say z is equal to 2r squared, for instance. Then what should be omega, the necessary angular speed, so that this object remains in the same horizontal circle? Because remember that b times r squared is like function y is x squared. Okay? So let me draw the picture now. So that these are the x, y, and z axes, and this is the curved wire, and here is the bead. What are the quantities? Remember that this is a function y equals x squared. But you can play with the steepness of this curve by multiplying by some number more than 1 or less than 1. For example, let's say this can be steeper, for example, y is equal to 2x squared. Or it can be flatter, y is equal to 1/2 x squared. So this number in front of the x squared term corresponds to the coefficient b, which we want to find. But in the opposite sense, as I said before, this function can be given directly, so b is known, but we are after the angular speed omega. So at which speed angular velocity should we turn the wire such that the ball, the bead, follows a horizontal circle of fixed radius. So this problem can be posed by two ways. But let's solve this one. Alright, this is the elementary part. So let's consider what is happening to the bead. That bead has a mass m. But we are interested in the velocities. Of course, the kinetic energy, potential energy of this, because we have to use the Lagrangian method. So part A says, write the Lagrangian for this case. Lagrangian is, remember, T minus V. Kinetic energy minus potential energy. But what is kinetic energy? It can have, of course, it has some velocities, but more than one component. In fact, it can have 3 independent velocities. One is, let me use the picture again, this configuration. For example, this is the position of the bead at any time. It can have 3 different velocity components. What are they? It is better to use cylindrical coordinates here, because spherical or Cartesian systems are not practical in such cases. This is a cylindrically symmetric problem. So we use those variables, r, theta, and z. This object, as it turns like that, consider this case. So this object, ball, has 3 independent components of velocity. One component is just along the radius. So it may have a velocity, because first we don't assume that it is turning in a fixed radius. We are free. So the object is also free. So the ball may have, in the most general case, 3 mutually perpendicular velocity components. One is the velocity component along the, let's say, radius. So this may be one component. It may be 0, it may not be 0. Second possibility is it has a certain z component, because up or down, it can move up or down, z dot. And the other one is, since the wire is turning around the z-axis, it may have also a component out of the board. So black one is because of the angular velocity omega. Red one is maybe it moves up or down, so that z dot, and the blue one corresponds to the radial velocity, because as it moves maybe from a lower position to a higher position, its radius distance from the z-axis changes, increases. So if it is moving, for example, if it is moving from the lower position to a higher position, its R dot component is a positive value. If it is moving downward, R dot is a negative quantity. Also, it may have some vertical, in the z-axis, so this may be in the z direction. And also because of this rotation, let's use this omega, it may have a velocity in this direction, and these are mutually perpendicular, because these axes are mutually 2 by 2, they are perpendicular. The object, the being may in general have 3 velocity components, and we use the cylindrical components. This is coordinates. Remember that we use cylindrical coordinates. What are cylindrical coordinates? R, from this one R, and that coordinate is Z, measured in the z-axis, R, and also if you see the projection, this is sweeping an angle on the xy axis, so that this corresponds to theta, R, theta, and Z. If the position of an object is defined by 3 coordinates, as usual, then it may have 3 different velocity components. If you use x, y, z system, Cartesian system, rectangular, it will be x dot, y dot, z dot. If you use spherical coordinates, which we don't here, it will have again, according to the radius from the center origin, not from the z-axis perpendicularly, but in this spherical, this is perpendicular. However, in the spherical case, it starts from the origin up to the object. Theta is the polar angle, the other phi is the azimuthal angle, etc. But this is not a spherically symmetric case, it is a cylindrical problem. Cartesian and spherical systems are not applicable. Yeah, they may be applicable, but it will be more complicated. So the easiest system here is the cylindrical system, and these are the coordinates. So the object in general has 3 velocity components. What are they? So this one, the velocity components are r dot along radius r. R times theta dot perpendicular to this system. If you join the z-axis with the wire, this is a plane, and this velocity component, which is r times theta dot, is that tangential velocity, r theta dot, tangential to the shaded area. Shaded area is the region between the z-axis and the wire. And finally, z dot along the z-axis. Okay, so let's write them first. Get the Lagrangian and then take the necessary derivatives, apply the second case. So, L is T minus V. What is T? Then kinetic energy. So we are now talking about, let's say, part A. The kinetic energy. The kinetic energy is 1/2 m multiplied by the first component squared plus the second component squared plus the third first component squared. Second one, r theta dot. But theta dot is omega anyway, it is fixed. Theta dot is not changing. However, it is also possible for this wire to get faster and faster around the z-axis, or get slower and slower along the z-axis. That gives another possibility, but that will be creating more complication. So that one m times r dot squared, r times omega squared, because it is fixed, r times omega quantity squared, and z dot squared. So this is the kinetic energy. Potential energy, you can choose this point as z equals 0 level, so that it has a height of mgz at any moment. It is m times g times z from the origin. But since z is given by a function, b times r squared, so z dot can be written accordingly, for instance. Since z is written as some constant and r squared, z dot is what? B is a constant, so z dot is simply 2b r dot. Because 2r is the derivative with respect to r, but also we need the time dependence of r, which is r dot. And z dot square will be substituted. So that t will be 1/2 m. R dot square is r dot. Plus r squared omega squared, alright. And third part is simply z dot squared. So we take the square of this of 4b squared, r squared, r dot squared. And L is therefore T minus V. So we have M over 2 R dot squared plus R squared omega squared 4B R and R dot all squared minus mgz. But z is not an independent way. It is written as, again, B times R squared minus mg b times r squared, b squared. No, b times, yes, there's no square here. It is just, so this part corresponds to our variable z along the z-axis. Alright, this is the Lagrangian. Now part B says, for a certain condition to take place, let's calculate B, because B is now unknown still. Part B is using Lagrange's equation. Let me rewrite it. d by dt, del L by del. What is the variable now? The variable is r. The quantity, of course, in the original equation we had x here, but there is no x appearing in this equation. What is the variable? There is only one independent variable, which is the radius r. Because theta, for instance, theta dot is fixed. That wire is turning at a certain fixed rate. Therefore, it is not independent. Z is also not an independent case. Z is in terms of r. Because the ball is constrained to move along this curve. The ball cannot go, the bead cannot go anywhere else. It has to remain on the wire, so that z is not an independent variable. Z depends on the distance r, just like this curve. This is not independent. If you choose 2, for instance, it will be if y is equal to just simply x squared. If you set x equals 2, y is 4. If you set x equals 3, y is 9. So they are dependent. Z depends on r. Therefore, here we will write the only variable and its time derivative r dot minus del L by del r without the dot. It has to be equal to 0. Now it is time to take the derivatives with respect to the coordinates and the derivative of that coordinate. Del L by del r. First, let's find the second part. del L by del R. As we look at the Lagrangian, there are second, third, and fourth terms that contain R. So M over 2 multiplied by, in the first there is no R, it is R dot. In the second we have 2R omega squared, so 2R omega squared. In the next one we also have 2 times 4, 8 plus 8 B squared R dot squared. In the next one we have also BR squared, so minus twice mg br, minus twice mg b times r. So only the 2's will cancel. Here we can cancel these. That's all. So let me rewrite it. Del L by del R. M times r omega squared plus 4 times b squared r dot squared, and next after m we have minus twice gbr. So this is del L by del R. What about the derivative with respect to r dot? Del L by del R dot. If we look at the Lagrangian, we only have the first term having an r dot unknown, first and third. So after m over 2, we have two terms. One from the first, 2 r dot. The other from the third, again a 2 plus 8 b squared r squared and r dot. Again we cancel these 2's. This becomes 4. So this becomes del L by del R dot, simply becomes after M, only R dot plus 4 B squared R squared R dot. But now we will apply the Lagrange's equation, so d by dt will act on this term, last term. So d by dt Lagrange's equation will be rewritten now. So d by dt applied on this. D by dt applied on m times the parentheses. Negative del L by del R, which is this expression. That will be 0 at the end. Now, let's take the time derivative of the first line, m. So we can cancel m's first of all. M's, let's cancel them. And if you take this thing, it will be r double dot. If you take one more time derivative, it will be r double dot plus 4b squared multiplied by what? Time derivative of these things. Derivative of the first times the second plus derivative of the second times the first, the same idea. So this becomes first 2r r dot times the other r dot plus first one r squared, the other one r double dot. And we continue with the lower line minus r omega squared and the rest. And that's equal to 0. Maybe there are some cancellations. first we can group them as, let's say, for instance, we can group the terms as, let's say, r double dot times something plus r dot times something plus r times something equal to 0. This may be one way of moving further. So there are two terms having an r double dot dependence, this one and that one. So let's start with r double dot. R double dot multiplied by 1 plus 4b squared and the rest. Because 4b squared is common. 4b squared 1 plus 4b squared times this thing, r squared. Plus r dot multiplied by, there's an r dot here and an r dot there. Let's see what they do. 4 times 2, 8. 8b squared. 8b squared. R dot squared. This is r dot squared. So they are, r dot squared. Those are r dot squared. So r dot squared multiplied by 8b squared r. But minus 4b squared r. So this is also finished. Now we are left with r's. R terms are this one. This is written, that is written. And the other one, as we see, plus r times minus omega squared. So minus, let's put the minus sign outside. R times omega squared. No, this is already minus, so therefore this is enough here. Put it there. Minus omega squared. Minus omega squared plus 2gb. And that's equal to 0. So this is the general expression. It seems to be a bit complicated. But according to our purpose, this is not all will be taken into account. It seems to be a complicated expression. Yes, indeed. R double dot times something, angular acceleration along the radius, linear speed along the radius, and some other terms. But what is our purpose? What was the problem telling us? It says that if it is turning at constant velocity, it is at constant radius. Since it is turning at constant radius, since the bead is turning at constant radius, what is that value? Not important. R is equal to capital R, for instance. If it is turning at constant radius, then obviously R dot will be 0 because there is no change in R. And automatically R double dot is also 0. So we are not interested in these terms. So we are left with only this term. And this R now becomes capital R. And we want to find the value of B. And this R is also not important. If this quantity has to be 0, inside of the parentheses should be 0. And finally, this quantity minus omega squared plus 2gb has to be 0. And we immediately understand that. Let me write it here. B, the required constant, has to be omega squared over 2g. Omega squared over 2g. So this has to be the number that determines how steep the object, the curve should be. For instance, this is a possibility for a certain b. This is another b. This is another b. Maybe more steep, like this. This is a greater value of b. If B gets less and less, for instance, it has to be flatter and flatter. Depending on the value of B, the steepness of this curve is determined. But let me also repeat that according to a different way of asking this problem, the opposite one could be, for instance, this B can be given, B is given as a known quantity. And then we can find what omega should be. Because if you turn this wire sufficiently quickly around the z-axis so that you may reach a point where this object doesn't find the possibility of moving up or down, so it remains in the fixed horizontal circle. But if you change omega to a different value according to a new purpose, if you want this ball bead to move upward, for instance, then it means its radius from the z-axis will increase, because as it goes upper and upper positions, the distance from the z-axis it is less now. As it goes upper and upper positions, then radius will increase. So r dot will be something positive. Then r dot can be specified by the problem, for instance. For this ball to get away from the z-axis at this rate, for instance, so r dot is given. Again, r double dot will be 0 because acceleration along the r direction is then 0. So if we neglect this first block, second block, this can be given also, specified by the problem, and then we can find the certain omega, for example. So these are different ways of asking and solving the same problem. So this is a good example of beads moving along the wires are a good part of the mechanical problems. Now let us apply our new tools, Lagrangian equations, to some other possibilities. For example, you may have a pendulum, normal simple pendulum. This simple pendulum has a certain length and a concentrated mass as a bulb at the end, and it makes oscillations. This is simple pendulum. And we have already written the equations and the solutions to this case, sinusoidal solutions, obviously. But now let's assume that some more complication is applied. For example, while this thing is making oscillations forward and backward, let's say that the other tip is not at a fixed position, but it is making maybe horizontal movements at a certain frequency, maybe very little frequency, so it takes more time to go from one end to the other end, and maybe very, very quick oscillations. Also, maybe the vertical motions at a certain omega, while this is making oscillations, maybe the other tip is going up or down. And in the more general case, while this pendulum is making oscillations back and forth, the other end is making circular motions. So while this is making maybe this kind of motions, the other end is making rotations in circular ways. Let's now analyze these possibilities and get some equations. Also, check the validity of the equations obtained at the end with the fixed end of the simple pendulum and see whether we obtain it correctly. The fixed end of a simple pendulum of length, let's say B, mass M, is now moving in a circular way. Is moving in a circle of, let's say, radius r, fixed radius r. Of course, if it weren't fixed, it would be much more complicated. If r also were changing, in the most general case, of course, it would be much more complicated. This fixed end, so we talk about, as I have tried to show you, this is the fixed end, that's the simple pendulum. But this end is now turning in a circular way while this is making forward and backward oscillations. And this length is, let's say, B, length B, but this radius is R, for example. And this is turning at certain fixed angular velocity omega. So this fixed end of a simple pendulum of length B, mass m is moving in a circle of radius r at a certain constant angular velocity omega. At a certain, and constant is important, at a certain constant angular velocity omega. So find the Lagrangian and get the equations of motion. So the given parameters are mass m of the bob, length b of the rope or the massless very light rod, and the radius r of this circle for the other end of the pendulum, and also angular velocity omega for this circular motion. So these are given quantities. Of course, g can be used. Velocity. Let's choose this system of x and y. X-y system is normal. Rectangular system is satisfactory because we don't need any spherical or cylindrical system. This is just normal rectangular Cartesian coordinates. Okay. Write the Lagrangian and get the equations of motion. Or let me draw the picture in a better way. So this is a circle, and at the end, at the center of this circle, we have the origin. For example, draw this rope, one end here, the other end there. So this is also important. That part is radius r, and this is turning at some omega. And at any time, this angle is theta, but that angle is, let's say, omega t. So there are two angles, two independent angles, of course. One is angle theta for a normal simple pendulum, whether or not the other end is turning. The other angle is, upper part is just omega t, which is continuously moving on a circle at equal time intervals at equal periods. Omega is the frequency, angular frequency of those rotations. Alright? And that is the 0, 0 position. So these are x and y axes. Now let us write the kinetic and potential energies of the ball, mass m. Okay. The kinetic and potential energies are the following. In order to write the kinetic and potential energies T and V for the pendulum, we should first write the coordinates x and y. the coordinates of the ball, because the mass is very light, other kinds of energies are absent. So we only talk about the kinetic and potential energies of the ball of the pendulum. Write the coordinates of the ball, x and y. So let's write x according to this origin, of course, with respect to the origin. What is the x value? As you see, there are two parts. So let me first draw that part again. So this is the circle. For example, that's the radius, and these are the xy coordinates. Okay, so here is the ball. But there are, as you see, two parts. One is this part, the other is this part for the x coordinate. But this part, since the radius is r and the angle at that position is omega t, okay, so this angle is omega t, therefore this part is r times cosine omega t. It's a triangle, right? Triangle. Hypotenuse r times cos omega t. Well, what about the other shaded part, the zigzag part? It is another triangle, but the length is, remember, b. And this angle is theta. This angle is theta. Now that is theta, yes. So b times cos theta. Sorry, b times sine theta. B times sine theta. So x is the sum of these two zigzags. R cos theta plus b sine theta. So x can be written here. X component is r times cosine omega t plus b times sine theta. Do we have to take it at this position? No, anywhere we can take it. So this kind of writing the positions is enough for us. Of course, if the ball is somewhere here, there will be sign changes, etc. But never mind, this is not important. So for this case where we can write it more easily, it is the sum of these two terms. What about the vertical position, y? Again, we can consider these. So we have such an upper part in this configuration and a lower part. So we have also this lower part. Therefore, we have to subtract from the positive one the negative. The negative will be subtracted from the positive. So y, therefore, y will be. What about this horizontal, zigzag? It is r times sine omega t. It is the opposite side. R times sine omega t. Please don't confuse thetas by omega t's. And minus this whole thing, which is b cos theta. Minus b cosine theta. So there are variables like theta, for instance, and therefore omega is also important. There are two motions combined. One is the normal back and forth oscillations of the pendulum. The other is the continuous rotations of the other end in a circular way. So these are the quantities we have to use for x and y. Now we will take x dot, y dot for the velocity, etc. Let's go very slowly and step by step. T is 1/2 mv squared. Sure. 1/2 m times v squared. But v can be written as the combination of x dot and y dot. Because v squared is x dot squared plus y dot squared. Remember the previous problem where we slide a bead along a wire. In that case, in this cylindrical system, since the wire was turning also around the z-axis, the object, the bead had three different possible velocity components. However, now it has only two because the system is moving on a plane. There's no motion from out of the board or into the board, so that what is happening is happening in the xy plane. Therefore, it has only two kinds of components: x dot, the other is y dot, and those x and y are written here. So T is simply m over 2 x dot squared plus y dot squared. Now let's therefore find x dot and y dot. Then x dot. First term, r is a fixed radius, so that it is cosine omega t becomes minus sine omega t, but don't forget to take the omega as well. So it is negative, we have an r, we have an omega, sine omega t from the first term. But the second term is b fixed, yes, but sine theta becomes cos theta, but also don't forget to put the theta dot. Remember, theta dot is not omega. Omega is the velocity, angular velocity of this part. Theta dot, omega is fixed. This part is turning, is sweeping equal angles in equal time intervals. However, here for the pendulum, it is theta dot, and it changes from position to position, angle to angle. So please don't confuse omega and theta dot in this case. Omega and theta dot are different angular velocities. One for the upper tip, the other for the bob or rope. Okay, this is x dot. What about y dot? Lowercase. Similarly, we have r omega cos omega t, r plus r omega cosine omega t, but from the second part, cos becomes minus sine, so it becomes positive, b plus b sine theta and theta dot. So these are the velocities in the x and y directions. But we have to take them squares, they're squares. So that t will be m over 2 multiplied by square of this plus square of that. So it will be a bit more complicated. So this is like a plus b, for instance, a plus b. So its square will be a squared plus 2ab plus b squared. Eh? So after m over 2, let's multiply it with the square of this thing. This one, please don't try to not to miss any variable, otherwise the result will be wrong. Square of the first, of course it is positive. R squared, omega squared, sine squared omega t. Plus or minus, we get middle term, minus 2ab. Minus r, let's first write the constant, r omega b theta dot multiplied by sine omega t cos theta. Sine omega t cos theta. And the last one, let's add it here, b squared theta dot squared cosine square theta. But we continue after m over 2, we continue with this square of the second part. That again, this is in the form of a plus b square, so that this one there is no dot here. R dot is impossible because R is fixed. First term squared, r squared omega squared cosine squared omega t, first one, plus twice the multiple product, plus twice, there's a 2 here. There's a 2 here if you forgot. So 2 here, r omega b theta dot cos omega t sine, just reverse. Cos omega t sine theta, when we continue with the square of the last, plus b squared theta dot squared and sine squared theta. Close the parentheses, close the parentheses. as we look at it, we recognize some similar terms. The first from the upper part, first from the lower part. So if you compare this one with that one, first parts are common, so sine squared plus cos squared, therefore this is 1. Similarly, if you look at the last parts, so this term and that term, if you compare them again, we have some common terms, cos squared plus sine squared, again 1. And middle part is also dealt with in a way. So we understand that t will be, after m over 2, r squared omega squared times 1, because sine squared plus cos squared. And similarly, plus the last part, b squared theta dot squared, b squared theta dot squared times 1 cos squared plus sine squared. But what about the middle part? We have again some common terms, 2r omega b theta dot, 2r omega b theta dot, 2r omega b theta dot, sine omega t cos theta, cos omega t sine theta. And we remember from trigonometric identities that sine, let's say a plus b, plus or minus b, what was it? Remember, it was sine a cos b, and according to the order of the signs, if it is plus, plus, yes, this is now minus, plus minus, cosine a, sine b, and it is similar to this. So write the middle block, 2r omega b, but should we choose minus sign or plus sign at the beginning? Let's choose this one, positive one. So we have plus, write it here, plus, plus, common terms, 2r omega b, 2r omega b theta dot, multiplied by what? Cos, sine theta, let's write the other order, sine theta cos omega t, sine theta cos omega t, minus cos omega t, sine omega t cos theta. Cos theta sine omega t. So this is like sine a cos b minus cos a sine b. So this can be abbreviated as sine of difference. Sine of, what is a? Theta. Theta minus omega t. So this is also substitute. So finally now we have t as first part and m over 2, 1/2 m, multiplied by the first two terms, r squared omega squared plus b squared theta dot squared, and the next part plus, after the first block, 2r etc., 2r omega b theta dot, we have sine theta minus omega t. Close the parentheses and close it again. So this is the kinetic energy of this oscillating system. What about the potential? Potential was already written there. Potential energy is, I will erase, but we can write it. Potential energy was m times g times which distance? Positive one, which is r sine omega t, r times sine omega t, minus b times cosine theta. So this was the position of this ball with respect to the origin. There's, in this configuration, for this photograph, I mean, in this case, right now, it has a positive part because of the circle and a negative part because of that. Of course, maybe later, this object will come somewhere here, so this one will also be a negative term, but for this case, this is correct. Now we should find the derivatives with respect to the r and with respect to theta and theta dot, for instance. because the lengths are not variables. There are two lengths. Length of this radius, which is fixed. Length of the rope is also fixed. So the only thing to differentiate is with respect to angle theta. Okay, so since the length R and B are fixed, because, for example, this rope is an inextensible rope whose length is fixed. If it were something like for instance, like a string, some elastic object, then its length, like a spring for instance, its length would be changing, it would be compressing and elongating, so that we would have to take another derivative with respect to the length of the rope, or of the string, or of the, let's say, spring. But in this case it is relatively simpler because those lengths are fixed. But the angle theta is changing, so we can take the derivatives with respect to angle theta. Since the lengths R and B are fixed, we should take the derivatives with respect to angle theta. So L is simply T minus V. Let me write the full form of L. L is of course T minus V. It is defined by T minus V, as we already talked about. So L is now full upper part minus the lower part. So L is M over 2 multiplied by this line. Negative the lower part, mg, and the rest. So this is the Lagrangian. And we will take the derivatives of L with respect to angle theta and theta dot, which is the angular speed for the pendulum. So del L by del theta. Let's start with the first term. M, after writing M over 2 multiplied by. Is there any term having a theta? Here, no. Here, no. We don't have theta here. Theta dot is, remember, something else. We will take it later. Here, we have only one appearance of theta here, so that write all the things twice R omega B theta dot, and this becomes cosine theta minus omega t. That's it. But there is one more appearance of theta which is there, so we continue with the minus sign, minus mg, there is nothing here, but it becomes plus b plus mgb, cos theta becomes sine theta. That's all. So we have two terms, upper line and lower line. What about del L by del theta dot? There are some cases, this one and the other one. So del L, let me write it there to see it better. Del L by del theta dot. As we look at the Lagrangian after m over 2, this term doesn't give us anything. That one, yes, 2b squared theta dot for the first case, and also there's a theta dot here. All the rest can be written there, plus 2r omega b sine theta minus omega t altogether. And here there is no theta dot. So these 2's can cancel maybe. So these 2's may cancel, that's all. But we now should apply d by dt to this expression, to this derivative. So let's now write that one. d by dt applied on del L by del theta dot. What happens to that? Now start with the first. Multiplied by b squared theta dot. Now theta dot becomes theta double dot. b squared theta double dot, first term. There's no 2's have already cancelled. Plus r omega b. Now how do we take the derivative? First we should take cosine. Sine becomes cosine. Cosine theta minus omega t. But it didn't finish yet, because we have to take the derivative of the inside, time derivative. What is that? And we should multiply theta dot minus omega. Theta dot is the time derivative for theta, minus omega is the time derivative of the second term. Minus omega. Close and close. And this term, from this term, we will subtract del L by del theta and set it to 0. This block, remember that d by dt of del L by del theta dot minus del L by del theta that we found there will be 0. So let's write it now over there. This block minus that block will be equal to 0, or this one equals that. So cancel the m's. Everywhere there's an m, so forget about these m's. We don't write them anymore, so that also these 2's have already cancelled. So this term b squared theta double dot plus the rest, plus r omega b multiplied by the last part, theta dot minus omega multiplied by cosine term, cosine theta minus omega t. Alright? So this thing, negative, what we see there, m cancel, 2's cancel, so this block plus that one, minus r omega b theta, r omega b theta dot cosine theta minus omega t, and also another minus sign for the rest, gb sine theta, minus gb sine theta will be 0. Alright, then let's open this one. Open this one. So b squared theta double dot plus, if you open the first one, r omega b theta dot and the cosine block, cosine theta minus omega t. Next, minus r omega b omega, another r omega b omega squared, negative, cosine theta minus omega t part, and then we continue. R omega b theta dot cosine theta minus omega t minus gb sine theta equals 0. But as we look at it, we immediately recognize that there's a cancellation. R omega b theta dot, R omega b theta dot, cos. So this term cancels totally this one. Identically, they cancel out. So we have the remaining blocks, this one, that one, the third one. So finally we get b squared theta double dot, b squared theta double dot. Next we have this negative term minus r omega squared b and cosine theta minus omega t, and finally minus gb sine theta equals 0. Maybe we can divide through by b, because there is b everywhere, so this b, that b, and that b cancel, because the right hand side is 0. And what else? We can immediately also divide by b, another b. We can divide by b squared, for instance. So that, without this one, let me directly divide by b squared. So divide by b squared, and b squared. Alright, so these b squares cancel. And this one cancels one of them, this one cancels one of them. So theta double dot, finally, theta double dot, negative r omega squared over b, r omega squared over b multiplied by this cosine block, multiplied by, and all is subtracted, minus g over b sine theta equals 0. So this is the expression obtained for this peculiar kind of pendulum, which is executing two motions. One as a normal pendulum, back and forth oscillations on the xy plane, and the other, because of the forced rotations at the top, this is executing some other kind of motion. So that this is the result. Now we can check it. Let me write a comment finally. A comment. If, for instance, there is no omega, if you stop this motion, it means there is no omega, because omega is the angular frequency of those rotations. If there is no rotation at all, so this upper end is fixed at a certain position, and only the simple pendulum is making back and forth oscillations, we should obtain the equation of a simple pendulum. If the upper end is at rest as a normal pendulum, as in a normal simple pendulum, okay? If the upper end is at rest, so there is no omega, then omega turns out to be 0. So what happens to our equation if omega is 0? As you see, there is an omega here, so there will be no middle term. Of course, this omega is 0, but before that we have another omega here. That omega will be 0, so there will be no intermediate term, and it reduces to the expected equation of a simple pendulum. Then omega is 0, and it reduces to the equation of a simple pendulum. Remember the simple pendulum's equation, theta double dot minus g over b sine theta. And again, after the cancellation of m's, for instance, yeah, this is the expected result. Of course, for small angle oscillations, if you keep this angle of oscillation around plus 30, minus 30, and if this angle is not very, for example, this is a different kind of rotation. This may be taken not as a simple pendulum, because this approximation cannot be applied. We apply the Taylor's approximation for small angles. Small means at most 30 degrees, because for 30 degrees, remember, if sine theta is pi over 6, for let's say 30 degrees, pi over 6, if you take pi to be 3.14, pi over 6 is approximately 0.52. And sine 30 is, remember, 0.5. So they are very, very approximate results. So until as large as 30 degrees, we can apply the approximation, but no further. However, for smaller angles, it is also quite applicable. Sine theta and tangent theta. Theta can be, so this is the case of small angle oscillations between plus 15 minus 15 degrees, for instance. So for such cases, of course, this approximation can be used, and then this sine theta can be written as theta, and we obtain the equation of the simple pendulum. Otherwise, if this upper part is also making some circular motion, then we have an additional term, this term. And for example, you may ask some other questions in this problem. For example, if the problem says, if omega is given as such a value, maybe 5 radians per second, whatever, then you will apply that one. R and B can be given. So this is also the value of the cosine for any angle theta and your omega. So this is also GB over B sine theta. And since it reduces to the expected result for the simple pendulum, it seems that we have found it correctly. But if, for example, by mistake, if we had a certain term, certain other term independent of omega, for example, let's say we have here, we forgot to another term, assume there is but there is no omega in this term. However, then by making omega equals 0, we wouldn't get rid of this remaining term, so we wouldn't get the expected equation for this simple pendulum. So it means we made a mistake. Or if, for example, we have another omega here, then by this setting, last term will also disappear, and just theta double dot equals 0 means theta dot is a constant. If angular acceleration is 0, angular velocity is constant, which means this is not a simple pendulum, but it is something turning continuously at a certain fixed angular speed. It is something totally different. So this validates our solution. Alright, this is the end of the problems where I tried to solve in the Lagrangian equation. There are, of course, several other applications of this. In the next case, we will pass to the momentum, linear momentum, some other cases, for example, that we didn't mention in the Physics 101 lectures, especially rocket motion, for example, because in the, remember, linear momentum, we use the idea that F external equals 0. If F external is delta V by delta T, if there is no external force acting on the system, angular momentum, linear momentum is conserved. But in the next lecture, we will have also some cases where even the mass is changing, so that it is not simply m dv by dt, but there is also a dm by dt term. So we will have a rocket. There are two parts, important parts. One is just the thrust of the rocket from the ground at the beginning. It has to have a large thrust so that it starts to move up from the ground, from maybe Cape Canaveral, for instance. And then during the motion in space, it will use some exhaust to move further, to change the direction. So we will, of course, in Physics 101, we neglected those cases where mass is changing. But now in classical mechanics, of course, we will have those cases as well. We will have some problems in that chapter in the next lecture.